in these few videos, we'll describe what monads are very briefly, and then their associated Kleisli categories, and we'll give a few examples, the most important of which being the Giry monad, which describes certain ideas from probability theory in a completely categorical language. So first we'll give the definition. Just recall the definition of a monad. And so C is a category. We'll fix our category C. And a monad on C is a triple. And it consists of a bunch of things, the first of which is a functor from C to itself. Let's call it T. And two natural transformations, one that comes from the composition of T followed by itself to T. Let's call that B. And then a third natural transformation, which we'll call delta, which takes us from the identity functor on C to T. And these three, this triple has to satisfy the following two commutativity conditions. Now, these are a little bit intuitive if you think about it. So let's imagine that we have one thing that we could do is take T and apply it to the category 3 times. And in this case, we'll have the following diagram of functors from C to itself. We can follow T twice. And in fact, we can follow it 3 times. And we can take these two by using B to get a single T. And we can follow these two to get another single T as well. But we could have also done this composition in a slightly different way. Instead of applying B to the first two functors T, we can apply it to the latter two. And then we can compose it with the first one. So this is a very natural sort of associativity condition. And B is sort of like the product. And this is telling us that the product is associative. So such that this and another commutative diagram that sort of tells us how this acts as the identity for B. So in this case, we can either have T itself. So here's the identity on C, and this is just T itself. So this is just a map from C to itself. We also know that we have this delta from the identity to T. Now we have T squared. We can apply B as well. And this gives us a functor, natural transformation from T to itself. But it tells us that if we plug in a delta, then that's supposed to be equal to doing the same exact thing, but in the opposite order. Namely, if we first did T, apply the identity here, and in this case, we apply delta on the other side, and then B. Then these two diagrams both must commute. Or in other words, this diagram equals this one, and this one equals this one. So this is a very abstract way of writing down a monad purely in terms of their pasting diagrams. I think it's going to be very helpful if we go through an example to see what all of this means. Now, the only slightly unfortunate thing about this example is that you do need to know a little bit about measure theory, which I'm going to assume you know for this video. So let's take C to be the category whose objects, so this for me denotes objects of C. And let's say that the objects are measurable spaces. So these are sets equipped with sigma algebras and not necessarily measures. So just measurable spaces. And the morphisms of this category, so these are the morphisms. are going to be measurable functions. So these are just measurable spaces with measurable functions. And we're going to define a monad T on this category. So first we'll define the functor T. So it's going to take, we'll call this P actually, because it's going to be easier for me to write P than it is T. And it's going to take a measurable space X with its associated sigma algebra to, well, it's got to give me another measurable space with another sigma algebra. And that measurable space is going to be the set of probability measures on X. So probability measures on X. And you could ask, what is a and I'll just call this Px. So these are the set of probability measures. What is the associated sigma algebra? I don't know what to call it, sigma Px, I guess. And the associated sigma algebra is the smallest one such that the functions, the evaluation functions, given any measurable subset of E, which is a measurable function on the space of probability measures on X, 2, 0, 1, is measurable. Are measurable for all measurable subsets of X. And what is this function doing? It takes a probability measure on X and it evaluates that probability measure on your measurable subset. So these are very natural functions, and you just want to make sure that for all of our measurable subsets, this map is measurable. Oh, such that the functions are measurable. So that defines a sigma algebra on the set of probability measures. And the rest of this functor is determined by what it does to a morphism. So if we have a map from one sigma algebra into another, what should T of F be, or P of F? Now, this is supposed to take us from probability measures on X to probability measures on Y. Let's call this PF. Now, if you give me a probability measure on X, what can I do with it? Well, I can push it forward to Y. So PF of a probability measure mu is exactly the push forward of that probability measure. Which just means that if you give me a measurable subset, don't call it E, maybe call it A, then the push forward evaluated at A is the measure of the inverse image of A. This is a measurable subset, so we can make sense of that definition. So this is what just defines the functor T. We still have to define B and delta. So delta is going to be a little bit simpler, so let's define that one first. And it's going to be a natural transformation from the identity. So give me any space X. So this was T. Now for delta, so give me a specific measurable space. So that's an X, comma, its sigma algebra. And this is going to be a map from X to probability measures on X. And you can guess what such a map should be. It takes a single element in X, and I need a probability measure associated with every element of a measurable space. And one such thing is the Dirac delta measure at X. So this is just little delta X. This is the Dirac delta measure at X in X. So it turns out that this defines a natural transformation. And finally, for B, what do we do for B? So in this case, if we apply B twice, so again, natural transformations are determined by what they do to objects. So if we look at a specific object x, then what we're doing is we're taking a probability measure on the space of probability measures of x, and we are constructing a probability measure just on x. So how do we do that? Well, let's take a probability measure on this big space. Call it bold face P, for instance. This is a probability measure on Px. Then what we need to know is what is, so this gives us a probability measure on just x. And so what happens when we evaluate a measurable subset of x? Well, what we can do is we can evaluate this for every single measure on x that's available. So what we can do is we can evaluate an arbitrary measure on our measurable subset E, and then we can use this measure to integrate all of these values. So this is dp evaluated at mu, and then we integrate over the space of all probability measures on x. So this gives us a sort of weighted average of the probability measures on our original space x. So it takes a probability measure on the space of probability measures, averages it out to construct a new probability measure on x. And it turns out that this is also a natural transformation, and in fact all of these functors and natural transformations define a monad on the space of probability measures. So in this case, P, B, delta defines a monad on the space of measures, on measurable spaces. And sometimes we call this a probability monad, but in some contexts it can also be referred to as the Giry monad. And in the next video, what we'll do is describe the Kleisli category of an associated monad and see what the Giry monad tells us about probability theory. You can already guess that there's some idea of probability going on just from this monad itself.